Hello everybody, welcome to the world of neural pruning. Today's topic of discussion is polynomials. Polynomials. If you're in class 10th, you would have wondered you've already come across polynomials in class 9th. Don't worry if you don't remember it. We will revisit those chapters and then get you to understand what polynomial actually is. Let me start with the word polynomial. So what is polynomial? Polynomial is a combination of two words, poly and nomial. Poly is a Greek word which means many. Nomial is terms. So many terms together makes polynomial. So why do we need to study polynomial? Polynomial is basically used in order to determine the graph curves. So let me give you a practical example. Everybody have gone through a roller coaster ride. Did you ever wonder how did the curves in roller coaster is made of? It is with the application of polynomials. Okay. Now, what is a term? Term is a combination of constant, variable and an exponent or a power. Let me give you an example. 3x square. So here, which one is a constant? 3 is a constant. Why 3 is a constant? Any real number becomes a constant. X is a variable. X can take any value. That's the reason we use x as a variable. And the square here is nothing but the exponent or a power. So under polynomials, we have various types of polynomials. They are monomials, binomials, trinomials, and like that till nth nomial. Now, what is monomial? The example that I quoted, 3x square, is a monomial because it consists of one term. Let me give you an example for binomial. 3x square plus 5x. So you tell me how many terms are involved here? There are two terms. If you wonder, 3x square plus 5x, I used an arithmetic operator plus in between 3x square and 5x. So in a polynomial, you can use arithmetic operators like plus, minus, multiplication sign and the division sign. Only thing which you cannot do is, you cannot divide a polynomial with a variable. This is the only exclusion. Okay. Now, if I use a term like 3x square plus 5x plus 6, this is called as just an expression. When I equate it to 0, then it becomes an equation. So 3x square plus 5x plus 6 is equal to 0 is an equation. So what type of polynomial is this example? It's a quadratic. Why quadratic? The highest degree here is 2. So it is quadratic. So have you ever wondered why we need to understand quadratic equations? Basically, quadratic equations are also used in order to calculate your day-to-day calculations. Let me give you an example. So assume that I am going to purchase a flat. Now to purchase a flat, before I purchase it, I need to know the area of the room, the area of the dining hall and the area of the kitchen. So have you ever wondered? We can use quadratic equation to calculate the areas. Similarly, I want to buy a used vehicle. So if I want to buy a used vehicle, after I purchase it, I want to understand whether I am on the profit or on the loss. I can still use here quadratic equations to determine whether I am on the profit or on the loss. Similarly, if I want to participate in a run marathon, if I need to win over the run marathon, then I need to determine at what speed do I need to run in order to win over the competition. So even there I can use quadratic equation. So let me introduce you to the polynomial world through our neural pruning community. So we have a wonderful lecturer called Madhusudan with over 10 years of experience. He has a passion in teaching mathematics. So now let us walk into the classroom of polynomial.
Hello everybody. Let us now deep dive into the area of polynomials. Okay, let us now focus our attention on the 4 examples listed on the board, and let's check whether each one of these happens to be a polynomial. The first one, 4x square y cube plus 3y plus 7. Okay, so this particular expression is a combination of 3 terms. Okay, basically it's a combination of 3 terms. So here 4, 3 and 7, okay, are constants, constant terms, and here 4 and 3 are also called as coefficients. Okay, coefficients are always combined with the variables. So here in this particular term, x square is a variable, y cube also is a variable. Okay, so basically this particular term is a combination of 2 different variables. So this is going by the basic definition of a polynomial. So this satisfies all the necessary conditions. So this is a term which is part of a polynomial. The second term 3y again is a combination of a coefficient with a variable, and the last term 7 is basically a constant. Okay, so this particular expression is a clear example of a polynomial. X square plus 4x plus 5. So now if you care to observe, there is a difference between the first expression and the second expression. The first expression is a multivariable expression. So it involves usage of 2 independent variables, x as well as y. On the other hand, the second example involves a single variable x. So this particular expression can be called a polynomial in x. Okay, so of course you can also represent this as, for example, a function in x, function involving x, so f of x. Okay, so this is a polynomial. And 2x minus 5. So here 2x minus 5 also satisfies the necessary conditions, a combination of a coefficient and a variable and a constant term, so separated by plus or minus signs. Okay, so this also is a polynomial. And finally we have written a constant term 4. So now this particular 4, number 4, you can also assume that it is multiplied with a constant term. Can we take it like this? So you need to think about this. Okay, so so this particular number is a constant, and this also clearly represents a polynomial, and we actually call it as a constant polynomial. Okay, so all 4 of these examples that we have listed on the board happen to be examples of polynomials. And there is something else that we could learn from these examples. Okay, as you have noticed in the first example, it has got 3 terms. Okay, and this has got again 3 terms. This has 2 terms. Finally, this has a single term. Okay, and based on the number of terms available, we actually have different names for all these expressions. For example, if there is a single term in a polynomial, this is called as a monomial. Okay, and then 2 terms, it is a binomial, and both of these examples have 3 terms each, so it is a trinomial. Okay, so now we have understood the basics of a polynomial, and we have also understood that a polynomial can be of different types: a monomial, binomial and a trinomial. So basically this monomial, binomial, trinomial, etc. are named based on the number of terms that we find in each one of these polynomials. Let me take two more examples in order to improve our understanding of the terms of a polynomial. The first one is, for example, x square and then another constant minus 7. Okay? So, in the first example, see now we have already discussed that a term is a combination of a constant, which is also called as the coefficient, okay, which is connected with the variable, and the variable can have powers or exponents. But in this particular case, the example taken is of a single variable, okay, x square. So, in the absence of a clear constant term, we take the coefficient as 1, which you are already aware. Okay? So, now x square is a variable, although it is a variable alone, still it qualifies to be called as a polynomial. Okay? In the second example, we have written only a constant term. Okay? So, it is basically a constant term alone that is represented here. Now, this particular constant term can also be referred as a polynomial. Okay? So, for example, you will be wondering on what basis we could conclude that this constant alone can be called as a polynomial. So, for example, minus 7 into x raised to the power 0. So, anything raised to the power 0 is 1. Okay? So, that way this is minus 7, and in spite of having written only the constant term, it still qualifies to be called as a polynomial. Having understood what kind of algebraic expressions could be referred as polynomials, we now need to understand in what circumstances some algebraic expressions do not qualify to be called as a polynomial. So, I have listed 4 such examples. Now, 3x into y raised to the power minus 2. So, now in this particular term, you have 2 variables x and y. Now, absolutely no problems with the coefficient 3 with the variable x. But as far as this exponent or power of variable y is concerned, we have minus 2. So, now all of you be aware that the powers or exponents of any variable associated with a polynomial must belong to set of positive integers. Okay? So, as you are all aware, you can have any positive number, okay, as the power or exponent of any variable associated with a polynomial. In this particular case, the exponent happens to be negative, and for this reason, this particular example is not eligible to be called a polynomial. Okay? The second example. So, now 2 divided by x plus 2. So, again, any variable associated with a polynomial can have only positive integers as exponents. Okay? So, now you will have to represent this as 2 multiplied by x plus 2 raised to the power minus 1 when this x plus 2 shifts to the numerator. Okay? So, again this negative exponent ensures that this particular example cannot be called a polynomial. Third case, 1 by x. Again 1 by x is nothing but x raised to the power minus 1. So, again on the same grounds, since minus 1 happens to be a negative integer, so this particular example 1 by x is not a polynomial. In the last case, root x, you can rewrite this as x raised to the power 1 by 2, and as you clearly know, 1 by 2 is not a integer, okay. So it cannot be called as a polynomial because the exponent does not belong to the set of positive integers. In order to improve our clarity on the concept of polynomials, I have taken 3 more examples. Okay, now we will check each one of these in order to determine whether each one of these could be called a polynomial. First case, it is x by 2. You can also rewrite this as half multiplied with x. Okay, so here the coefficient is 1 by 2. Okay, so now let us clearly understand the second condition associated with the definition of a polynomial. This particular number 1 by 2 is basically you can call it as a real number. Okay, it belongs to the set of real numbers. Okay, now based on the actual definition of a polynomial, these coefficients associated with variables that are part of a polynomial can belong to set of real numbers. Okay, so now half 1 by 2 as coefficient is perfectly alright, it is acceptable because 1 by 2 belongs to the set of real numbers. So for this reason we can call this as a polynomial. Okay, in the example that we have just discussed, see, some of the students could get confused. Now in the earlier example, okay, I think it was root x and I had written it as x raised to the power 1 by 2. Okay, so now 1 by 2 as a exponent of a variable is not permitted. So you have to be clear on this. So this exponent can only be positive integers. You can't have negative integers, you can't have rational or irrational numbers as exponents of a variable. Okay, and as far as the coefficient associated with the variable is concerned, this coefficient can belong to or it must belong to the set of real numbers. Okay, so for that reason 1 by 2 as a coefficient of a variable is permitted. On the other hand, 1 by 2 as the exponent of a variable is not permitted. I think this point is clear. So now I have actually used the terminology set of real numbers. So some of you could be wondering what exactly is this set all about. Okay, so now this set of real numbers actually includes integers. That is, integers, when I mention integers, it includes 0. Okay, so 0 also is included. Okay, then you have rational and irrational numbers. Okay, so set of real numbers, you can have positive integers, negative integers, 0, rational and irrational numbers. So when I discuss about real numbers, I am stressing it once again. So this particular definition is it is applicable only to the coefficient associated with a variable of a polynomial. So on these grounds, this 1 by 2 as a coefficient is perfectly alright. So this particular polynomial, this particular example could be regarded as a perfect example of a polynomial. Okay, coming to the second example, if you have understood why the first example qualifies to be a polynomial, so you will appreciate that this is a similar example, right? So this is 3 by 8 into x. So x is a variable, exponent is 1, so perfectly alright. 3 by 8 is a rational number. So we have already observed that rational numbers are part of set of real numbers. So for this reason 3 by 8 multiplied with x or 3x by 8 is a perfect example of a polynomial, which can be rewritten as 3 by 8 multiplied with x. Now x has a exponent of 1 which is permitted, and 3 by 8 is 3 by 8. When we carry out actual division, it works out to 0.375. So this is a terminating kind of decimal representation. So for this reason, this is a rational number. Okay, any rational number after normal division, if we get a terminating decimal representation, then it is called as a rational number. So for this reason 3 by 8 belongs to the set of rational numbers, which in turn belongs to real numbers. So 3 by 8 x can be called as a polynomial. In the last of our examples that we have taken up, the number is root 2. Now root 2 happens to be a irrational number. Okay, 2 is not a perfect square, so square root of an imperfect square, that is 2, belongs to the set of irrational numbers. Okay, so when I call it as an irrational number, what I mean is, for example, so when we carry out actual division, so this continues. Okay, so now this decimal representation, what we observe here is that it doesn't terminate at all. Okay, this is point number 1. It doesn't terminate. That's why it's called a non-terminating decimal representation. Secondly, you don't have any block of numbers that repeat or recur. Okay, so it is non-repeating and non-terminating. So this is the basic definition of a irrational number. Okay, so now root 2 is an irrational number, and irrational number belongs to the set of real numbers, and we have already observed that the constant term or the coefficient of any variable could belong to set of real numbers. On this basis, root 2 could be called as a polynomial. In the next set of examples that you see on the board, the first of which happens to be the constant 4. So we have already discussed about regarding any constant term as a polynomial. Okay, so now this particular number 4, we also observe here that it is not associated with any variables. So there is no variable that we find in this particular example. So this is an example of a polynomial with no variable at all. So it is still qualifies to be called a polynomial. In the second example, 4x square minus x. So we find that this particular polynomial is a polynomial in terms of x. So there is a single variable associated with this polynomial. So this is an example of a polynomial represented using a single variable. In the third example, if you care to observe, you have x, you also have y. Okay, so in other words, this is a combination of two variables. So what I am trying to highlight through these examples is that you can have 0 variables, you can have a single variable, you can have 2 or more variables also, and all of these examples still qualify to be called as polynomials. The next stage, let's examine what's special about polynomials. Okay, so now 2x square y, okay, plus 4x square y plus 7xy. Okay, all these are examples of polynomials. Okay, as a whole, this is a polynomial, okay, with 3 terms, or you can also regard them as being 3 independent polynomials. Okay, whatever it is. When we look at this particular expression, we notice that the variable associated with the first 2 terms happens to be the same. It is x square y, x square y. So these are called as like terms. So when we add two expressions or polynomials, we can add directly, okay, just as we add two numbers, okay, whenever we have like terms. So 2x square y plus 4x square y is 2 plus 4, 6x square y, okay. As far as the third term is concerned, 7xy, so this particular, you just focus your attention on this, xy is different from x square y, xy is different from this x square y. So xy and x square y are regarded as unlike terms. Is this clear? xy is different from x square y. For this reason, xy and x square y are referred as unlike terms, okay. So you have to represent it separately. You cannot combine a like term with an unlike term, okay. So when you add up two polynomials, you get another polynomial. In the next example, we are examining the concept of multiplication of two polynomials. So as you observe, this is also a polynomial, this also happens to be a polynomial by itself. Now when we try to multiply two polynomials, okay, now what we have to do is, we have to multiply the signs. When you don't have any sign mentioned, it is taken as a plus sign. So plus into minus is a minus, followed by multiplication of the coefficients. 2 multiplied by 5 is 10. X square multiplied with x is x raised to the power 2 plus 1, and y multiplied with y square is again. So when we simplify this, it becomes minus 10 into x raised to the power 3, followed by y raised to the power 3. So if you look at the result of multiplication of two polynomials, it is quite clear that this also happens to be a clear example of a polynomial. So what we can conclude is, when we multiply two polynomials, we get another polynomial. In the next section, we examine division of one polynomial by another. So we'll just find out whether we get a polynomial in division of polynomials as well. So the example taken up is 9x square plus 12x plus 1 divided by 3x. Now this is a numerator is a polynomial. The term in the denominator also happens to be a polynomial. So now when we actually divide numerator by denominator, you could write it as 9x square by 3x plus 12x by 3x plus 1 by 3x, okay. So now 9x square by 3x is 3 goes 3 times, so 3x. Now since x square and x, they are not together, x square happens to be in the numerator, x is in the denominator, so you have to subtract the exponents. So that's what I have done. So this is x raised to the power 2 minus 1, followed by 3 goes 4 times in 12. So this x and x cancel out each other, you are left with 4, and then 1 by 3x. Now I would request all of you to focus your attention on the resulting polynomial, okay. So now this is 3x plus 4 plus 1 by 3x, okay. So now 3x is a polynomial, 4 also could be regarded as a polynomial, okay, but 1 by 3x, you will have to represent it as 3x plus 4 plus 1 by 3 multiplied with x raised to the power minus 1, because x in the denominator, when it shifted to the numerator, you get a negative exponent. So as we have already discussed in the beginning, you cannot have negative exponents for the variables of a polynomial. So for this reason, this particular term ensures that the resulting expression is not a polynomial. So what do we understand from this example? It is that addition, multiplication of two polynomials invariably result in a polynomial. So the final conclusion after taking up all these examples is that addition, subtraction and multiplication of two polynomials invariably result in a polynomial. On the other hand, from the example that we have just discussed, division of two polynomials may or may not yield another polynomial. In some cases, you could still get a polynomial, but there are exceptional cases such as this, when the resulting polynomial or the resulting expression is not regarded as a polynomial. Let me just add this last point here. Although we have not discussed examples of subtraction of two polynomials, please be aware subtraction of two polynomials also result in a polynomial.